name is Andy Pimentel, University of Amsterdam, and I have the pleasure to introduce the first keynote speaker of this conference, Professor Tulika Mitra. She's a professor of the National University of Singapore, where she leads a group that performs work on very different aspects of embedded systems, ranging from low power, so energy efficient computing, heterogeneous computing, application-specific computing, and software performance analysis for real-time systems. Well, she's well known in the embedded systems community for that work. She also published a lot in that field, over 100 papers. She is involved in different journals as an editorial board member. She has been the program chair of many of our top conferences in the fields, like ASP DAC, I think, MSoft, and what was it? There's another one, I think. Anyway, let me invite Tulika to give a great speech today.
Thank you, Andy. Thanks for the kind invitation. It's really my honor to be here in a conference that's so steeped in history, as well as such a beautiful place. So I'm going to talk about cooperative embedded heterogeneous computing, unity in diversity. I actually saw that there is a lot of talks on heterogeneous computing in the conference program, as well as Keynote on Wednesday by Peter Hofsky and a special session. So let me kind of just get started by explaining what heterogeneous computing means in my context. So what we are looking at is really sort of application processors which are in the form of a system on chip. This is really embedded computing that comprises of different kinds of computing elements. These computing elements can be different kinds of processors which are very different in terms of our performance characteristics. The GPUs, the DSPs, the reconfigurable computing, and today we are even seeing the accelerators, like for example neural processing units. And why there is like so much interest in heterogeneous computing at this point in time? Well, there are a couple of reasons. First is that of course the Moore's law is continuing, and so what you are seeing is really like a large number of transistors on chip. So if you look at the Apple A11 Bionic chip, the system on chip that's there if you have an iPhone X, then it has 4.3 billion transistors, and that's really amazing considering what a small device it is. So that part is continuing. We are having large number of transistors, but what's not happening is that we are not seeing the power scaling that is supposed to happen with every technology generation. So there is a failure in terms of Dennard scaling, and because of that, what you are seeing is that you can have large number of transistors on chip, but you cannot really power them on at the same time. So this phenomenon has been dubbed as dark silicon because a significant percentage of your chip is really sort of dark or not usable at any point in time. And the estimation is roughly by 2020, we are probably going to see 90% of the silicon is going to remain dark at any point in time. And that has hit hard the mobile and the wearable computing space even before desktop and the server space, simply because you do not have any cooling solutions in those devices. And you are looking at thermal design power for these application processors roughly in the range of 1.5 watts to 2 watts. So really you have a very little margin to play with, and that makes this problem very difficult. But of course in the embedded computing space, we are really kind of great in terms of converting a problem into an opportunity, and we never give up. So what happened is that people saw, well, this means that what you have is that your area is not costly anymore because of Moore's law, but your power is really the challenging part because of failure of Maynard scaling. So you can actually spend the area in order to buy power. And that's exactly what is happening with heterogeneous computing, because you realize if you are just going to put the same cores again and again, so if you have a large many-core architecture with homogeneous cores, and you are not going to be able to use 90% of those cores, then you are really wasting your silicon area. Instead, what you could do is that you could kind of just have different kinds of heterogeneous computing elements on chip, and then given an application, you are just going to pick up the one that is most useful for you, that is more power efficient for you, that is most performance efficient for you. And that leads to significantly improved performance and energy efficiency, and that's what heterogeneous computing gives you. And I'm going to classify the heterogeneous computing along two different directions. The first one is kind of obvious, which is functional heterogeneity, where you have compute elements which are very different in their nature, in terms of how you program them, how you use them in software. So these are, for example, the CPU and GPU are very different, the DSPs are very different, the accelerators are very different. So these are functional heterogeneity. And you can see them, so this is a mobile processor from Qualcomm called Snapdragon 835, and if you, I don't know whether you can see it from there, but you will see that it has the DSP, of course it has the GPU, it has different kinds of processors, and as well as audio processors, security processors, and so on. The other one, which is kind of has become very prominent in mobile computing, and at this point any mobile SoC, pretty much state-of-the-art mobile SoC has this, is the performance heterogeneity. So performance heterogeneity is when you have processors which have the same instruction set architecture. So if you write a program, you can run it on all these processors, but they are very, very different in terms of their performance and their power characteristics. And this all started with really ARM big.little architecture, even though now everybody, including Apple, has very different kinds of this kind of heterogeneous computing. And this again, I'm showing you the Qualcomm Cryo 280 CPU that's present in the Snapdragon, and it has kind of high performance compute cluster, which is on the left. So this one is very high performance, but also high power consumption. On the other side, you have the small cluster, which has sort of the small in-order cores, which are not that powerful, but they are also not that power hungry. So really, depending on the application, you want to use the architecture that is most suitable for you. And there is really abundance of heterogeneity at any point, at this point in time. If you look at the mobile SoCs, starting from Apple, which also has a neural processor inside, to Huawei HiSilicon Kirin 970, which was the first one to have a neural processing unit on chip, along with the GPUs and the CPUs and the security engines and ISP, which is the image processing part. To Samsung Exynos chip. And of course, Xilinx has its UltraScale Plus, which has the CPU, the GPU, as well as the FPGA. And with the rise of eFPGAs, you are more or less going to see more SoCs with FPGA embedded inside, other than really Xilinx and Intel FPGAs. So we have these really wonderful, beautiful architectures that are very powerful, and that's really an amazing feat from the architect's point of view. But I come from a computer science department, and what is interesting or curious to me is that hardly anybody in my department is aware even that a mobile computer has a GPU that can be programmed. That includes my colleagues and my students, right? So there is this very big missing link between the software developers and the hardware. So we provide this wonderful hardware, but the software folks just don't know how to use them, and so they give up. And so what we have been doing in my group for the past 5 years or so is kind of trying to bridge this gap between hardware and software. And we are trying to really make it easy for software developers to take advantage of heterogeneous computing and make it transparent to them as much as possible. And so I really look at it as kind of best of times from the architecture side, of the hardware side, and worst of times from the software side. So let's see whether we can make it better. So what are the kind of dilemma that a software developer will face if he or she looks at really this kind of a complex architecture? So first of all, you have so many different cores and accelerators there. Which one should I use? The second is that can I actually use all of them together in some way? And if I do that, how do I actually manage to keep the power below the thermal design power limit? And how am I going to maximize the battery life, which is of course important in any mobile or wearable computing space. So let's start with the first one, and I'm going to look at it from the point of selecting the code between the CPU, the GPU, and the FPGA. Of course, one can extend it to include the DSPs or the other accelerators. And now, if you look at this problem, what we are really trying to ask is that, okay, so I have a piece of code. Which of these accelerators is most suitable for my piece of code? And you might think that this is a really easy problem, but it is not, as you can see from a couple of talks today morning as well, because as a software developer, I'm actually more familiar with a sequential programming language like C or C++. I'm maybe willing to do a little bit of multi-threaded programming, and if I'm able to do that, then I can actually easily get the performance of my code on a, let's say, ARM big dot little architecture. But when it comes to GPU and the FPGAs, it becomes really challenging. So let's first start with FPGAs. And if you look at the FPGAs, you will say, well, you know, there are high-level synthesis tools. For example, Vivado HLS from Xilinx. So I just give you this piece of code. You can run it through HLS tool, and you can get the code that should run on the FPGA. It is partially true. So what happens is that, of course, you get a piece of code that can run or you get a bit stream that can actually run on the FPGA and that can produce correct result. But the reason that you are trying to use an FPGA is not to get the correct result, but you want performance. And if you want performance, that doesn't happen so easily, because even as a software developer, then you need to get involved and understand how FPGA works. And for these tools, you have to provide, for example, a lot of different pragmas. You have to tell the tool, okay, how many loop unrolling, how much loop unrolling should I do? Should I do loop pipelining? Should I do array partitioning? So these are kind of things that only hardware programmers are kind of aware of. And so it's extremely difficult for somebody without that experience to figure this out. Same for the GPU, you have to take this piece of code and then you convert it into CUDA or OpenCL, and then you can only you can run it on the GPU. So not only you need to kind of parallelize the piece of code, but also figure out what are the optimizations you need to do in order to get the performance that you are interested in. So we looked at that problem and we sort of tried to change it a little bit, and we said that can I give this recommendation that given a piece of code, which is the reference code in a sequential C, so there is no optimizations done, no parallelization done, and can I automatically tell you that this is the accelerator that is going to be most suitable for you? And then, of course, once you know that you have to use the GPU, then of course you have to put in the effort in order to actually maximize the performance on the GPU. But even then, what we do is that we provide insights to you. So we tell you that these are the kind of optimizations that you should do in order for you to get the best performance out of this piece of code. So we developed a couple of these performance estimation tools, the Lean Analyzer, which is for performance prediction for FPGAs from sequential C or C++, really any kind of code that can convert into LLVM IR. CG Predict, which is a performance prediction tool for GPUs, and we also provide, as I mentioned, the performance insights. So I'm going to give you a very high-level description of these tools, and since we are all here, I will be happy to talk about each of these in details later on. So what we do really for the performance estimation is that we take a piece of C code or C++ code, we convert it into LLVM intermediate representation through the compiler. We take a couple of representative program inputs, and we actually run this at the IR level. From this, we get this trace, which is the LLVM IR trace, and this trace is really a dynamic trace. This trace is processed by our tool in order to extract out the kind of things that are important and necessary, and then we create a dynamic data dependency graph. So this is not the static data dependency graph that the HLS tools will use, but rather a dynamic data dependency graph, and then we actually try to do a very quick scheduling in order to figure out how many cycles this code is going to take on an FPGA. We have made this tool available through GitHub, so if you are interested, you can actually go ahead and try it out. So how well does it work? So let me just show you one simple example. So this is actually a 3D convolution code, here you can actually use different kinds of optimizations. You can do loop pipelining, loop unrolling, array partitioning. Now for each of these configurations, traditionally what you are going to do is that you are going to invoke the Vivado HLS and figure out that what is the performance. Now Vivado HLS is very unpredictable in terms of how long it takes in order for you to synthesize a piece of code into circuits, right? So it can take anywhere between seconds to hours. And if you have, for example, for this piece of code, you have a design space which consists of 128 design points. If I run HLS tool on each of these points, it's going to take roughly 10 days for this particular example, and even then it did not terminate. Instead, what it linearizes manages to do is that it actually manages to pinpoint what is the best configuration for this piece of code and what is the expected performance within half a minute. Now, this seems like magic, but it's not magic if you think about it this way, that we are not really synthesizing this piece of code. So we are not giving you an RTL code that you can run on the FPGA. We are simply telling you that these are the configurations you should use, and then you have to go back and use whatever high-level synthesis tool you have access to in order to actually synthesize that. But then you are doing the high-level synthesis only once as opposed to multiple times, which gives you significant productivity improvement. Right, and our accuracy is pretty good, so we are roughly about 2% away from the optimal configuration, and our design space exploration time is down from, on an average, about 30 hours using HLS tools to only a couple of minutes using our tool. And then the same concept is kind of applied for the GPU performance, and again we start with the sequential C code, we go through the LLVM IR, we have the dynamic trace, and then we manipulate this trace in order to extract out the different words. So this code is not parallelized at all. We, in our tool, is automatically, we are parallelizing this into different words and blocks and so on. And then we model, of course, the computational performance, but also in this case, the memory performance, because for the GPU, the memory hierarchy was very important for us. And then we can actually give you an estimate of the performance of these applications. And again, our accuracy is very, very good, about 2.66%, and it takes roughly about a couple of seconds in order to get the results. And not only that, we can provide different kinds of performance insights. So for example, whether you should do blocking for this code or not, how exactly you should go ahead and parallelize these, how many blocks you should have, and so on and so forth. So all these things can be provided by our tool. So really it takes away the pain point from the software developer, and then the software developer can go ahead and actually just try to convert it into real CUDA code. And most importantly, as I said, we started off with this hope that given a piece of code which is written in just a reference sequential C or C++, whether I can actually tell you which one is better. Is GPU better or an FPGA better? And as you can see here, we are very good in predicting exactly which one is more appropriate for a piece of code. And our estimated time is most of the time very close to the actual time that it is going to take to execute this program on that particular accelerator. So that was pretty good, but then we realized that even though in these examples you see that there is a clear winner in terms of which accelerator is better, in certain applications, and certainly for example, neural network applications, we saw that you cannot really kind of come up with a clear winner, and sometimes it makes sense for you to engage multiple of these processing elements in a program. And how do you go about doing that? Well, in the mobile space, the only way for us to go about doing that is really using OpenCL. So OpenCL is an open standard for cross-platform parallel programming on CPU, GPU, FPGA, DSP, you name it, right? And if you are familiar with CUDA, it's very similar to the CUDA programming model in the sense that you really launch multiple very fine-grained threads, and then you run this application using those threads. What we really wanted to do is that so normally what people would actually do is that you take an application, you figure out which part you want to implement on the GPU or the FPGA, and then you convert that part into OpenCL code and you just ship it off. What we said is that it actually makes sense even for just this kernel, you can actually partition the kernel so that you can give certain percentage of the threads, let's say to the CPU, certain percentage of the threads to the GPU. And here we are actually doing it on both big.little architecture as well as the GPU. So some part of the threads, some threads go to the CPU, some threads go to the GPU. And this was really a lot of engineering effort to make it work so that the same kernel can be executed on both of these concurrently. But if you do that, the actual benefit is quite nice. So over here, what I'm showing is for different applications, you have two performance numbers. One is for running it on the CPU and one is for running it on the GPU alone. Now if you take the best of these two, best of the CPU time and best of the GPU time, and then you take the same kernel and partition it transparently using our tool to run it on both the CPU and the GPU without putting in any effort whatsoever as a software programmer, you get 20% performance improvement compared to CPU alone or GPU alone performance, which is very nice. Right? And so you can again then do a lot of optimizations. Here I'm not showing any optimizations we did for either the GPU or the CPU, but if you do those optimizations, your performance mileage will actually be higher. And then we tried the same kind of thing with CNN. So this is kind of darknet, which is a very small CNN that can really fit into the mobile application processors. And this is actually running on Xilinx Z-board Zinc, which is a very low-cost SoC. And what we have over here is that typically you will take the convolution kernel and you will actually run it on the FPGA. But instead of just running it on the FPGA, what we are doing is that we are actually taking advantage of these neon cores in the CPU. So ARM has this vectorization unit called Neon, which is fairly efficient in actually running the convolution kernels. So what we have is really an operating system layer on top, which takes these kernels and then splits it up into small processing units. In this case, these are matrix multiplications. So you have these very small matrix multiplications. And then you sort of have a work-stealing algorithm that is actually distributing them onto the FPGA and the processor in order to get the best performance out of it. And we really kind of managed to get very high energy efficiency and performance out of these things. So this is just showing you how much advantage you can get if you have this cooperative heterogeneity where you are trying to take advantage of both sides. So the baseline is really just running on the CPU. So if you start using the neon cores over there, then you see about a 2x performance improvement. Now this was our optimized neon implementation. I think the ARM Compute Library right now has a neon implementation which might actually be a little better. And then you get about 7x if you just use the FPGA but do not use the neon. And this blue bar is when you start using both the neon and the FPGA, and you get about 8x to 9x performance by using all of these things. So really, what I'm trying to get at is that there is a lot of opportunity to be had if you actually try to use all the different components on chip in a nice way. But there is a problem. So once you start using that, then you get really excited and you say, hey, I'm going to use all the things that I have and let's kind of distribute the work across all these processing elements and let's see what happens. Well, you get into trouble. Why do you get into trouble? You get into trouble because remember that the reason we started with heterogeneous computing is because of dark silicon. We did not have enough thermal design power in order to switch on all the cores. And now if you start doing that, then you get into the same problem that we had earlier, which is that you hit the thermal limit. So here I'm showing you this Samsung Exynos 7420 SoC, and you see this is the big cluster of CPU, this is the small cluster of CPU, and this is the GPU. And if you add up the power consumptions, if you run each of them at the highest frequency level is about 10 watts. Now, no mobile SoC can go beyond 1.5 to 2 watts. So that means that if you do this, you are just going to trick this whole thing, and then you are going to go to sleep, and so that the chip can cool down. And if you are, let's say, running a gaming application, you are going to see really huge jitters if you are trying to do your gaming. So what you really need to do is that if you are trying to use all of these different things, then you need to think about how to really do the power and thermal management on these mobile systems or these embedded systems, which is heterogeneity aware, so that you can stay within the thermal design power by actually switching the frequency level of the different cores, and in case of big dot little kind of system, by doing migration from one core to another depending on what your application's requirement is. Now, one of the advantages, and this is the one that we took a lot of advantage of in these kind of works, is that we are talking about really kind of user experience. And so if you are looking at a mobile application, for example, gaming applications, you do not go beyond 60 frames per second, okay? Even if you can actually process 74 frames per second, it doesn't make any sense for the user, because the user is perfectly happy with 60 frames per second. Beyond that, for the human eye, it does not make any difference. So really, we are trying to keep it at that quality of service. We are never trying to go beyond the quality of service, and that's how we actually save power and energy. Now, once we started doing that, and so this one we started actually with gaming applications, and what we realized is that if you look at, and that was true back in 2015 and 2016 when we were actually looking at this problem. So if you look at the Android linear operating system, you will see that the CPU governance that manages the CPU frequency is completely independent from the GPU governors, or in this case the GPU device drivers that manage the GPU frequency. And so there is no coordination whatsoever between these two. But you are running the same application. So what it means is that you actually end up hurting the system performance as well as actually bump up the total energy consumption quite significantly. And so all we had to do is really sort of design these coordinated power management solutions that was looking at the whole application as a whole, figuring out, at which point in time the CPU is doing more work, and at which point in time the GPU is doing more work, and kind of manage the frequency of those systems accordingly. And that's how we actually managed to get significant improvement in frames per watt. So we got 20% frames per second per watt improvement simply by actually kind of managing them in a coordinated fashion. Of course, it involved a lot of modeling of how the system works and so on and so forth. But at a high level, this is really a very simple idea that works perfectly well. And going forward, of course, Linaro has changed things. And so right now, if you see at the Samsung processors at least, you will see that there is greater coordination between the two, which is very similar to what we have been doing. And then we took the same concepts and we actually had to solve the same problem for thermal management. And this is a bit tricky because predicting temperature turns out to be a little bit more challenging than predicting the power. This was actually a collaborative project with the Professor Jörg Henkel's group at Karlsruhe. And what you are seeing here is that we are actually, so we have a thermal camera with a lot of different cooling systems in order to cool the chip from the bottom, because we took out the heatsink from the top, so we couldn't really run this chip anymore. So we had all this, a lot of interesting engineering effort to put this thing there. And then we looked at the chip, and you can see clearly that sometimes the CPU is really getting hot, sometimes the GPU is really getting hot. And we use this camera in order to actually characterize the chip and figure out what exactly the thermal behavior is. And following that, of course, in the real system, we do not have the camera, so we use that model in order to do a coordinated thermal management. And then again, we get similar 20% improvement in frames per second over Linux. And the reason being that in Linux, since they do not do any thermal management, you just get a lot of jitters. So you hit the thermal limit, then you go down, you hit the thermal limit again, and so that's really, really bad. We reduce the peak temperature by about 6 degrees, but more importantly, we also even out the temperature variation. So we have hardly any temperature variation compared to Linux, which had about 10 degrees centigrade temperature variation, which is very, very bad for reliability. So that brings me to the end of this part of the talk, where we really wanted to talk about how we try to bridge the gap between the hardware and the software in terms of the heterogeneous computing. How much time do I have? Okay. So then let me switch gear a little bit and okay, so yeah, so we also kind of did this power management for big dot little architectures where you could actually, so previously we were just doing the voltage and frequency scaling, but here we have an extra knob that actually allows us to migrate our task from the big to the small cluster and back if we want to, in order to save energy. The only concern is that it takes lot of time and wastes a lot of energy if you make a wrong move from big cluster to small cluster or otherwise, because the migration cost between clusters is in the order of milliseconds. So you don't really want to do it that frequently, and you have to be careful about how you go about doing it. But if you can do it well, you again get rewards for that. And so over here, what you are seeing here is that I'm looking at the quality of service. So this is H.264 encoder, or I think decoder, I cannot remember which one. And this gray part is really the quality of service that we are interested in. So remember that I'm actually trying to take advantage of the quality of service. Now this red part is really if you are running this on the big cluster, if you are running this piece of code on the big cluster. So what immediately should kind of jump out at you is that you are most of the time actually exceeding the quality of service requirement, and so that means that you are meeting the deadlines, but your actual energy consumption is very high, about 2 times as opposed to if you are running it only on the small core. So this green part is if you are just running it on the small core, but again what you can see is that if you just run it on the small core, most of the time you are actually below the quality of service requirement. So even though you are saving power, you are not doing that well. And this blue part is our transparent scheme that is actually switching between the small core and the big core. So sometimes it is running on the small, sometimes it is running on the big core. But it is always meeting the deadline, and its energy consumption is somewhere close to the small cluster, even though it is giving the performance of the big cluster. Right? So that's what I mean by transparent migration in order to exploit this heterogeneity. And this actually leads to significant performance improvement. So this work was done back in 2013, 2014. That time the Linux governor, right now the Linux governor is more sophisticated, but that time using our technique you can get performance improvement compared to the Linux governor, simply because we are actually tracking the quality of service, but Linux does not. But at that point in time, we had put the TDP at about 8 watts deliberately, and so you can see that the Linux governor average power consumption is about 6 watts, whereas we were at, we had many different techniques. Some were reactive, when you see something bad is going to happen, then you take action. Sometimes we were proactive, and you can actually cut down the power consumption by almost half using these techniques. Okay, so sorry. So let me just now sort of switch the gear, and so for now we talked about this mobile heterogeneous computing, where we had these wonderful chips, and what we were trying to do is kind of bridge the gap between software and hardware. Of course, we were looking at mobile computing for a while, and then the next natural step was to start looking at wearable computing. And if you think about it, the wearable computings are sort of poorer but hotter cousins of the mobile computing, right? And what is interesting is that a lot of them are actually software programmable at this point. So your smartwatch, it can actually be programmed in software to run many different applications, and so is maybe your smart glass, and so on and so forth. So these are software programmable. And because they are software programmable, what you are seeing is that they are sort of following the trend that we have seen in mobile computing space. So you are seeing increasing number of cores in these devices. It's really amazing. At this point, you can find some of these devices with 8 cores, right, for your smartwatch. But what is not happening is that you are not seeing that much accelerators out here. There are some GPU accelerators which are like nano GPUs and so on, which are like really, really tiny, but they are not very powerful, and they are meant to do only sort of graphics and not do the programming part of it, right? So when I started looking at it, we sort of decided that, okay, let's try to see if we can do something about it, and we can actually introduce accelerators into this kind of system. And first we wanted to see is there a need for it, okay? So we started with a very simple application. I mean, we had a lot of applications, but this one was, I thought, very simple, is that we were trying to actually recognize the gesture, right? So for example, if you do like this, it means A. If you do like this, it means B, right? So you can actually kind of sort of write letters using this. So this is finger gesture recognition. And we were running it on TI sensor tag. And it turns out that you need to be able to do this in real time. You have to meet this 10 millisecond deadline per gesture. However, we were taking 131 milliseconds to do it on this ARM Cortex M3. Now, of course, you will say that this is a very simple processor. It is, but this is what is available here, which is 9 milliwatt at 48 megahertz frequency, and you get about 6.6 MIPS per milliwatt. So this is simply not capable of doing the kind of things that we wanted to do. And I mean, there is a reason why we wanted to do these things here. This is not a good application to tell you why it is important, but if you are doing healthcare monitoring or other things where people really do care about privacy, then instead of sending things to the cloud, you really want to do it or in situ on the wearable devices, right? So then we started actually looking at, instead of utilizing heterogeneity, we actually wanted to synthesize heterogeneity for these kind of systems. These are really ultra low power SoCs, and we wanted to see that whether we can actually go ahead and synthesize heterogeneity in these kind of systems. And very early on, we realized, or we sort of decided that we don't really want to create different kinds of accelerators. We instead want to create so-called universal accelerators that can be used by all the different application domains. So we really don't want to kind of, come up with a new SoC for each different domain, but rather our accelerator should be usable across different application domains, right? And it should be completely software programmable so that it can be used across domains. And whether we can do better than FPGA, of course, that was the goal, right? So one of the first attempts that we did is this thing called iCube. This is really an accelerator for IoT devices, so it's very, very tiny. It's actually a coarse-grained reconfigurable array, and I'll tell you in a minute what coarse-grained reconfigurable array is. And it actually manages to get less than 10 milliseconds per gesture. It's 63 MIPS per milliwatt as opposed to 6 MIPS per milliwatt, which was for the Cortex M3. And in fact, we also compared it with Samsung's CGRA. So Samsung has this CGRA called Samsung Reconfigurable Processor that's present in a lot of Samsung chips. And we get about 2x performance power improvement compared to that system. So what is this accelerator? Well, this is a coarse-grained reconfigurable array, which is just a set of processing elements. So you can see here it's a 4x4 array. Now, each of these processing elements is really a very simple ALU in some sense, right? But it can be programmed, so every cycle you can actually decide what instruction you want to execute, and it has a very tiny instruction set. But also you decide how to route the result of one processing element to another processing element, right? So you actually kind of configure both the routes as well as the processing elements in this CGRA every cycle. And of course you kind of try to accelerate the loops here, so that means that you have like just a set of instructions that gets repeatedly executed on these CGRAs, right? Now, the difficult part of the CGRA is, of course, and why it is not so popular is really because the application mapping is extremely difficult. So you start with the data flow graph and you have a representation of the CGRA, and you figure out that where each node of the CGRA should be mapped, not only spatially but also temporally. So in this case, for example, this one is mapped using 3 cycles, and this repeats again and again and again, right? So this is what the compiler has to do in order to figure out how to actually program the CGRA. Now, we figured out that one of the reasons that it was difficult to program the CGRA was not so much mapping these nodes into the CGRA PEs, but really routing these edges. So for example, if you have mapped here and the next dependent instruction is mapped here, so this multiplication is dependent on the addition, you actually need to route it over here, right? So this routing actually makes this problem very difficult compared to really the mapping. And in the route, what happens is that you make stops every single step all the way, right? So in this case, in order to go from here to here, you are going to take 3 cycles as opposed to, if you need to go from here to here, you can actually do it in the single cycle. So we tried to attack this problem in high cube architecture. So what we have here is really sort of bypassing. So if you need to go from here to here, we actually do switches in a way that is asynchronous bypassing. So if you don't need to actually kind of stop here, but rather you are just passing through, then you don't kind of use the route. You don't stop here. Instead, you just bypass this thing and you can fly through multiple hops in one cycle. And what is the advantage of doing that? So for this piece of code, this is the data flow graph, you can see that if I actually map it on the conventional CG array, then I need 3 cycles per iteration, whereas if I map it on high cube, I can actually get away with 2 cycles per iteration, simply because I do not need to have these extra routing nodes over here. And that makes actually my compilation also extremely easy compared to what I would face in a conventional CG array, right? So the architecture is very straightforward. So really what you have is a crossbar, and this crossbar is programmed every cycle in which direction you want to go. And if you don't need to stop here, then you have asynchronous repeaters, so you can just fly by. So if you look at the chip, this is really tiny. So this is 0.8 cross 0.8, 0.64 millimeter squares at TSMC 28 nanometer. This was the synthesis and place and route results. We actually taped out this chip this March from TSMC 40 nanometer process. And this is the chips, and you can see this on a board. Right now we don't integrate it with the CPU, but we are actually putting it on the TI sensor tag and connect it through the SPI interface. But of course, going forward, our goal is to put this and the CPU together. And if you look at the performance and power, so this is comparison of the ARM Cortex-A5 Xilinx low power FPGA, Samsung reconfigurable processor, and high cube. Of course, Xilinx is doing much better in terms of performance, but this is a more powerful chip. And similarly, you can see its power consumption is much higher compared to us. But if you look at the mix per milliwatt, we are actually doing much better compared to almost all the other architectures. So that was good, but as previously some speaker talked about, this needs to be connected. This is a loosely coupled accelerator, so it needs to be connected to the processor. And when we actually try to run our real applications, we face this communication bottleneck problem. And so what we wanted to do is that we wanted to see that if we can kind of integrate these accelerators in the processor much more closely, so whether we can kind of weave in these accelerators in our many core chips. And so the first thing that so these are actually made for ultra low power wearables. So first thing people ask me is that, why are you thinking of putting many cores on an ultra low power wearable? It just doesn't make sense. Well, it doesn't make sense if you actually put these power hungry cores there, right? But what we are trying to put is that we realize that there is a lot of parallelism. So this is the finger gesture recognition application that I talked about earlier, and there are multiple threads that can actually run in parallel. So you can easily create 16 threads. And so the many core architecture makes sense there, but because my power budget is so low, and I'm really talking about sort of 0.1 watt kind of power consumption, so I cannot really afford to have very complex CPUs. So here we are actually using these ARM Amber cores, which are simple 5-stage in-order pipeline. They're really, really small, tiny processors. So that's how I actually managed to keep the power budget within limit. And so each core should be simple. But once you put these cores as very simple, then the problem is that they don't give you the performance that you need. So you need to do the acceleration, and we do this acceleration using custom instructions. So each processor has sort of a very simple fabric that can actually be reconfigured in order to execute custom instructions. And I have been looking at custom instructions for a while, but the difference here is that we are actually kind of these are reconfigurable custom instruction units that can be reconfigured by the programmer, by the software, in order to implement different custom instructions on the fly. And so our first attempt at doing this was a 16-core chip, and then it had this configurable custom instruction fabric associated with each of the cores. We used a message passing programming environment because that was much faster and more power efficient compared to actually doing things in a shared memory fashion where we had to worry about cache coherence and things like that. And we also used so this is work with my colleague who was at MIT and then moved to NUS. So she had this smart knock which can do this fly-by-wire kind of thing where you can go from one core to another distant core in one cycle. So we use that smart knock over here for the message passing. So this is a little bit bigger chip compared to what you saw with the accelerator, but remember here we have both the processing, normal processing as well as the acceleration, and it gives us 1.7x performance speed up and 45% power reduction compared to the processor that you have 4-core in LG Watch SoC. But what we realized when we actually designed this particular chip is that your accelerator was fairly big. So what happened is that our accelerator was consuming a lot of area compared to the processor, which was tiny, and compared to the router, which was again not very big. So you are really kind of spending a lot of area in order to do this acceleration. So we wanted to see if we can do better than that, and what we did is that we looked at the kind of kernels, the accelerators that are required by the different kernels, and as expected, each of these different phases require different kinds of accelerators. So again, you have this need for sort of heterogeneity. So you have these different heterogeneous accelerators. And so what we said is that, well, okay, let's actually put different kinds of accelerators. So instead of making all the accelerators identical, which is what we did earlier, we actually had different kinds of accelerators for each of these different cores. But still we were not getting the performance that we wanted, and then we said, oh well, because each of these is really, really tiny, so they cannot do much, but I can actually fuse them together at runtime in order to create bigger accelerators and bigger custom instructions. So really, physically, you have very simple heterogeneous accelerators, but at runtime, you can fuse them together nicely in order to get better performance. So this is the switch architecture. We call it switch because we were switching the patches together. Each of these patches is polymorphic, so you can actually kind of implement different custom instructions using a patch, and then the patches can be switched together in order to create large virtual accelerators for complex custom instructions. And if you look at the performance, so you can see, for example, this one and this one, this is actually borrowing the accelerator from this guy in order to accelerate itself, and you can do something like that for different cores. If you compare it, so this is again for the finger gesture recognition application, and this is the normal variable, this is the speech without doing the fusion, and this is speech, and we can actually make the deadline, and the power consumption is about 139 milliwatt. We of course have all of these works have compilers that can actually take the applications and actually convert them into the program that switch can run. At the end of the day, if you compare it with a many core that does not have custom instructions, we have 2.3x throughput, 1.7x power efficiency, 2.88x area efficiency, but by area efficiency, I really mean performance per unit area, not in terms of total area. But what is most interesting to me is that my area overhead compared to many core architecture without any accelerator is only 0.5%. So that's really very, very small. So we can actually manage to kind of take advantage of this kind of an heterogeneity in a cooperative and synchronized fashion in order to get what we want without paying the cost. If you compare it with wearable SoCs, again, you know, average 1.6x throughput at 27% power. So this is actually, we are comparing against Qualcomm Snapdragon, which is the one that is there in a lot of mobile, smartwatches, and 6x in performance part. Okay, so to summarize, what we really what I wanted to get across is that heterogeneity in embedded systems is inevitable because of technology trends, but you are required to have both architectural and software support in order to improve the performance hardware for these systems. And as I see it, I think this is an exciting area, and I hope we can work together in order to meet all the challenges and take advantage of all the opportunities. So I see this talk really as an introduction, and I hope to talk to some of you during the course of this conference, and then we can chat about what we can do better. I'd like to acknowledge all my collaborators and the funding agencies. And finally, this is the last message. I think we were in the sort of homogeneous computing phase. This is, if any of you have been to Singapore, this is Marina Bay Sands, right? It's an iconic building, but it's very, very homogeneous. Right? And if you try to move to heterogeneity, in the beginning you might end up with something like this, which is heterogeneous, but probably quite not useful. And then I hope that we can actually move towards something that is heterogeneous, and that actually gives you the performance and power improvement that you really wish for, without actually giving you the pain, both from the software side and the hardware side. Thank you very much.
Time for a couple of questions.
I have a question. So you said that you take the sequential code, you make a recommendation how C should be executed. Are the developers one who are actually making the code parallelized? Or do you also help with that?
No, we do not help with parallelizing the code. So for example, for FPGAs, if you give me a piece of code, I will tell you that this is the pragmas that you should use. So in our case, we were using Vivado HLS, but in other cases, it will be different. So we actually give the settings for the different pragmas that will give you the best performance. Then all you need to do is set the pragmas, and then the HLS tool will give you the result that you need. But for GPU, yes, you need to be able to parallelize it. But we help in terms of, we say that, okay, you know, you need to have so many thread blocks, you need to have, you know, what should be your memory blocking factor, and so on and so forth. So all these configuration options we will give, but for GPU, you need to parallelize the code, yes.
Just one quick question. Did you maybe have ever a situation where, because of the synchronization that is necessary, the code which is made parallelized is actually slower on the target hardware than the sequential one?
Yes, that is possible, yes, absolutely. But because we were looking at individual kernels, so if we start looking at the total application, yes, this is the problem that we will face. But at this point, it was the kernel which did not require the synchronization. But yes, that's true. The synchronization will mess up your things. But for GPU, it should be actually not that challenging. Yeah.
I wonder if you have users using the tool, software guys using the tool, and what's your feedback?
For the FPGA, yes, for the FPGA we have made this available, and some of my colleagues who are actually working in application development, they have used it. The problem is though, we were looking at the kernel, okay? But once you try to actually map an application, it's not just about the kernel. You have to do this communication between the software and the hardware, and that part we do not take care of. And even if you use Vivado HLS, it's actually fairly complicated for you to get that part right. So that's where the problem is, not with respect to our tool, with respect to what.
No, but the user usually, I need a question, and by the way, thanks for the great presentation. I forgot the name.
Thank you.
But my experience too is that most users, software guys, they do not want to abandon the operating system. And that brings a layer of extra problems for people providing tools to IQD.
They don't want to, sorry, I didn't get.
They don't want to get rid of the operating system. They really want things to be a service like they are used to.
Right, but we are not changing any operating system out here.
No, but that's the point. But how do you communicate your tools with the operating system and
Okay, no,
are running?
Okay,
How is it seen in virtual memory, for example?
Okay, so if you are talking about our estimation tool,
No, yes.
the estimation tool, the goal is not to provide a complete solution. The goal is to just tell you that which accelerator you should concentrate on. Yes, so it's a zoo of accelerators, and we are just saying that you should pick this one. After that, you have to do your optimizations. We are just helping you, giving some hints and so on. But it's not a miracle.
Yeah.
Yeah.
I'm curious, is voltage frequency scaling still relevant?
For the mobile computing space, I do think yes. Simply because if you look at the kind of applications that we were running, and I think in the mobile space, if you are running 3D game, that's probably the most power-hungry application that you are running, because you are using both the CPU for doing the AI part and you are using the GPU for the rendering part. If you do that, if you don't do voltage frequency scaling, it just isn't going to work. You are going to trip all the way all over the place. You just hit the thermal limit. So voltage and frequency scaling in the mobile space, I personally feel it's impossible to get rid of. But I didn't get the question in terms of where you are coming from. What is the alternative?
Well, it seems like it's getting less relevant than it used to be, just because of technology, margins that we have, right? Yeah, we don't have as much voltage range as we used to have. But a related question I actually had was that if you look at big little, right, in an ideal case, I guess the low end of the big core at the lowest frequency would be close to the high end of the little core at the highest frequency.
Yeah.
I haven't played with this, but
yeah, you are right. And so I think the common question is that why do you even need two different microarchitectures in order and out of order? Why can't you just kind of use dynamic voltage frequency scaling all the way? And I think Intel, for a long time, I have talked to them, they refused to go into this big dot little kind of architecture simply because they felt that there is no need and they can actually cover this entire space using this. But I can tell you that even though there is a small overlap, the kind of improvement you get from voltage scaling, frequency scaling versus in order out of order is sometimes very different. So you can actually cover a larger design space using these in tandem, as opposed to if you were just kind of relying on frequency scaling. Yeah.
thank you.
Kirby?
A short one, the data dimension. So first with the CG array, you communication network infrastructure and also the arithmetic operations are fixed size, right?
Yeah, so for the CGRE that we designed, it's fixed point arithmetic.
Yeah, it's fixed point, but of a certain fixed predefined size.
That's right, yeah. We actually use 32-bit. Yeah.
Yeah, do you think that adding some kind of configurability in the data sizes
Yes.
will give you something?
Yes,
You
yes.
don't have to go bit level like FPGAs, right?
Definitely. In fact, when we were designing HiCube, David Atienza's group at EPFL, they were looking at a CGRA where they were actually doing SIMD processing in each core. So essentially, like 32-bit, you actually break it up 8 bits times 4, and that's a very cheap way of getting performance improvement. So we can do that in HiCube as well. And certainly, I mean, if you have 8-bit applications, that will certainly give you significant improvement, but we didn't do this for the demo.
Performance, so I think that you can save also a lot of energy.
Yes, you can. You can switch off the other parts, and then the network also. Actually, our network is also reconfigurable. You can select the bit width that you want for the network, so you can actually save. I should not call it network, but the links. Yes, in the switches, yes.
And then the second part of the question is now if you look a bit at the application level, this was the first part of the talk, where you look at the different heterogeneous accelerators and then you kind of statically assign which phase of the application should go where. I think that for certain systems, not quite sure for the wearable this is the case. Depending on the data that has to be processed by certain accelerator, you may change your decision where to send that specific to be performed on the system.
Right. So I'm sorry for the misconception. I'm not doing static mapping. So we are actually, so if you do the, we can actually dynamically migrate the workload from, for example, from big to little and little to big. And the performance gain that we are getting is because of that migration at runtime. And the kind of applications we were using are like media applications, and you can imagine what you said, that because of the input data, the kind of image that are coming in, the workload is very different. So if you are looking at like just my face, which is not changing much, then you can actually kind of go for the simpler core, and then when the workload actually becomes higher, then you move to the bigger core. So we were actually doing it dynamically, and certainly you need to do dynamically. But for the wearable, the architectures that you are seeing, we do not have space, or rather the power budget to do things dynamically, and at this point it's very simple. Yeah.
So that was your short question?
Yes.
Any other question?
Short one.
Final question here.
Is the execution trace the only input that you take to this? Or you take some other input as well?
Of course, the execution trace is the only input that we take from the application, but we need to do characterization of the architecture. And we do a lot of micro benchmarking, which was hidden here, in order to get really, like, the characterization of the system. And my students are really, really wonderful that they could do all these things so that I can come and talk here.
Right. Okay. So let's thank Tulika.